In this video I'll show you how I built a metal lathe out of second-hand materials which came from our local scrapyard. I live in an area where high-tech equipment is manufactured, so you can often find industrial materials like linear guide rails, lead screws and gears and lots of scrap metal from which you can build all kinds of stuff. The main spindle was a custom-made part. It is mounted with 4 tapered roller bearings which sit in rings that are mounted to a front and a back plate that form a housing that is mounted onto the lathe bed. Then come the pulley, the belt and the 3 horsepower motor that came off an old treadmill. The motor is mounted on the top plate of the housing. The spindle head matches a chuck that I also found on the scrapyard. It has 130 mm diameter and 30 mm boring hole. The motor control also comes from the treadmill, which I modified to include a speed control with tacho feedback and a small display to show the RPM. The main carriage rides on 20 mm linear bearing rails which are 60 cm long with 4 roller bearing blocks. A 12 mm steel plate is mounted onto the blocks and the carriage is moved by a long lead screw which I can turn via a handle on the rear plate. The cross slide rides on 15 mm linear bearing rails and 4 blocks and is also moved via a lead screw. The tool post is mounted with a pivot bar on the cross slide plate. The tailstock is made from thick aluminium that can grip and slide on the 20 mm rails. The tailstock spindle is actually a 30 mm square aluminium bar which is moved by a linear gear and a small gear which can be turned by a handle. The spindle slides between 2 aluminium blocks. For higher force, a threaded rod can also be used to push the spindle towards the chuck. An old drill chuck can hold the drill bits or a live center. I used digital calipers for measuring the carriage, cross slide and tailstock movement. These are handy because they can be zeroed at any position and remember the zero position. The whole thing measures around 1 meter by 40 centimeters, so it does not take up my whole working bench space. It weighs around 85 kilograms and still can be moved to the side of my bench when not in use. The lathe bed was made from 2 arms that came off a scrapped pick and place machine. Of course, some cutting and drilling was needed. The floorboard was made from 18 mm high-grade multiplex. The arms are bolted together and then bolted onto the floorboard. Here I'm checking the flatness of the base. Some spacers were needed under one arm to make the bed flat. Then the arms were bolted tight together. Lots of metal needed to be cut for this project. I mounted an abrasive disc in my circle saw to cut more accurately. I used a drill press for drilling holes. For tapping thread, I first mount the tap in my drill press and turn the chuck by hand to make the thread start straight. Then I use a hand tapping tool to complete the thread. To accurately drill holes in multiple metal pieces, I first glue 2 pieces together with cyano glue and then drill the hole through the bottom part using the top hole as a guide. After a lot of cutting, drilling and tapping, I finished the bottom plate, front plate, side plates, top plate, carriage plate, cross slide plate, front plate and tool holder. First I mount the bottom plate onto the front and rear plate. Then the left plate and right plate are mounted. It is very important that the front and rear plates are at 90 degrees from the base. The bolts construction allows for slight adjustment. Then the housing is bolted onto the lathe bed. Here I mount the tapered roller bearing outer rings to the front plate. It needs to be very secure, so I used 8 bolts. The rear bearing rings take less stress, so 4 bolts are sufficient. Now the main spindle is mounted. It needs the front taper roller bearings, securing ring and tightening nut. Then comes the 90 mm thread mill pulley, which has a key slot. Then comes the rear taper roller bearing and the pulley belt from the treadmill. After the first bearing nut is screwed on, the last taper roller bearing can be mounted with the securing ring and the bearing nut. To center the bearing outer rings, first loosen the bearing ring bolts and then tighten the front bearing nut and then the rear bearing nut. Then the bolts of the bearing rings can be tightened. The chuck is mounted onto the spindle with 3 bolts. Note that the spindle main head still needs to be faced. Now the 20 mm linear guide rails can be mounted. The horizontal lead screw has Acme thread with 4 mm pitch and 2 bronze nuts that can be tightened to reduce backlash. It is mounted with 2 bearings to the base rear plate. Now the carriage plate is mounted onto the linear bearing blocks. It is important that the carriage plate is at 90 degrees to the linear rails. The carriage can now be bolted to the lead screw nuts. The lead screws have right-hand thread, so I added a gear for making the carriage move towards the chuck when turning the handle clockwise. The gears came from an old copy machine. I get 3 mm carriage movement per turn of the handle. Now come the 15 mm linear bearing rails for the cross slide and the front plate of the cross slide. The cross slide lead screw is the same type as the one controlling the main carriage. It is fastened to the front plate with 2 bearings. The bronze lead screw nuts are bolted firmly to the cross slide top plate. The second bronze nut of the lead screw will help reduce backlash. It is pulled to the first nut with 4 screws, which need to be adjusted to get minimal backlash but still allow easy rotation of the lead screw. The top plate is then bolted onto the linear bearing blocks. The cross slide also needs gears for moving the tool holder towards the chuck when turning the handle clockwise. For the cross slide, I used a higher gear reduction ratio to get around 1 mm cross slide movement per turn of the handle. The tool holder is made from 6 metal plates. The 3 top plates are bolted together and the other plates are fixed together with steel pins. The tool holder rotates around a 12 mm rod, which is screwed into the cross slide top plate and can be locked via a nut with a handle. The cutting tool is secured to the tool holder via 3 bolts. By adding spacers below the cutting tool, the tool cutting head can be adjusted to match the chuck center line. Here you see the motor and speed controller that came from an old Kettler Marathon treadmill. The treadmill also includes an inclination motor and a big control panel for setting speed, but these are not needed for the lathe application. I reprogrammed the microcontroller to make the system more suitable for the lathe. On the primary side, the 230 volt AC voltage is rectified to around 320 volt DC, which supplies a standard step-down circuit that controls the motor voltage via a pulse width modulation PWM signal that drives the high voltage switch. The longer the switch is on, the higher the motor voltage and the faster the motor will spin. On the secondary side is a microcontroller that generates the PWM signal and sends it to the driver IC via an optocoupler that provides isolation. The microcontroller has a speed set input for the manual setting of the motor speed via a potentiometer. A disc with holes is mounted on the motor shaft, and a light bridge measures the motor shaft speed. This signal is also fed to the microcontroller. The control loop is very simple. First we read tacho in and the speed set signal. If speed set is higher than tacho in, we increase the PWM pulse width. If speed set is lower than tacho in, we decrease the PWM pulse width. Then we return to the beginning. The control loop is not fast, as it takes time to measure the tacho input, and I'm using 10-bit PWM resolution. But this is not critical, because the motor has a big flywheel that will handle most of the load transients. As I rotate the motor, you can see the tacho signal generating pulses. I added a small display, which will show the motor status, the spindle RPM set value, and the spindle RPM when the motor is running. The slow control loop will also give the motor a soft start, due to the slow increase in PWM duty cycle. The top plate has 4 bolts that serve as motor mount. After the top plate has been bolted onto the spindle housing, the motor can be mounted on top. Via the nuts, the motor height can be adjusted to tension the belt. When all is level and the belt is sufficiently tight, the nuts can also be tightened. I built the control electronics in an aluminium box, which is bolted to the side of the spindle housing. The motor wires have a connector that plugs into the control box. The connector can be reversed to change the rotation direction of the motor. It is important to ground the system because the motor is running from primary side and has quite some capacitance to ground. After plugging in the mains, we can switch on the unit for a test run. In stopped mode, we can dial in the desired RPM, and after flipping the switch, the motor speed will increase to match the set value. You will notice that the inserted steel rod end is wobbling a bit. This is because the spindle head has not yet been phased after installing. You can see this by using a dial indicator on the spindle face. After phasing the spindle head, the dial indicator now is very steady. Now we can check the runout of the system. After some adjusting of the chuck, I get around 0.05 mm of runout near the chuck, which I think is okay. When moving the dial indicator across the length of the steel rod, we get about the same runout, which is good. Now I check the side of the steel rod with the dial indicator to check if the carriage runs parallel to the chuck center line. When moving the carriage to the end of the rod, the dial indicator moves around 0.1 mm. This can easily be corrected by shifting the carriage linear guide rails slightly. After this, the carriage now runs perfectly parallel to the chuck centerline. The tailstock is made of thick aluminium plates and bars. To cut the aluminium, I use a sharp carbide-tipped blade in my circle saw. I spray some WD-40 on the blade and the object before cutting. It's a bit scary, but it works quite well. After a lot of cutting and drilling and tapping, here are the parts for the tailstock, including the chuck from an old hand drill. I glued a 4 mm rod in the bottom bars that fit the linear guide rail. To grip the rails, 2 bolts will clamp the bars to the rail. Here I'm assembling the bottom section of the tailstock. Now the front rail guides are added. They can be pulled together via 2 bolts. The guide on the rear rail will keep the tailstock steady on the linear guide rails. It can move freely, but when the 2 guides are pulled together, the tailstock will grip the rails and will not move. Here I mount the linear gear on the tailstock spindle bar. The handle that moves the spindle goes through some bronze bearings and the spindle bar side block. The small gear is fixed to the shaft with a steel pin. Now everything can be mounted on the tailstock top plate. The tailstock has a steel backplate with an M12 hole tapped into it. An M12 threaded rod can then push the spindle bar from the back for more force. After some greasing, the whole thing can be assembled. The top assembly is then bolted onto the bottom section. First I check whether the tailstock spindle moves parallel with the chuck center line. I adjust it to make it as accurate as possible. Then I drilled an 8 mm hole through the complete spindle bar and drilled a bigger hole for the chuck shaft. The holes will now precisely match the lathe chuck center line. Now the chuck shaft can be pushed into the spindle bar. It is a tight fit. Then the chuck can be pushed onto the shaft. Then the spindle can be mounted into the top assembly again and the tailstock is finished. The lead screw and linear rails should be kept clean from metal chips. I therefore built a flexible protection sheet. I cut metal strips from a thin metal sheet that was originally a printed circuit board stencil sheet. After lining up 20 strips with 1 mm spacing in between, I taped them together on top side with heavy-duty packing tape. And then I also taped the bottom side. They can fold together like a harmonica. On the lathe, I added Velcro strips to the spindle housing and on the main carriage. I also added Velcro on the harmonica sheet. To make the harmonica stay in folded shape, I heated the sheet a bit. Now the harmonica sheet can be fixed in place between the spindle housing and the carriage. The cross-slide lead screw and linear rails should also be protected, so I added a thin protection sheet as well. For the other side of the carriage, I made a harmonica sheet as well. Now the lead screw and rails are well protected from metal chips. The taper roller bearings must also be protected from metal chips. For the front bearing I made a protection cover from 6 mm foam board that can be folded open and fixed around the bearing ring. For the rear bearing I made a fixed cover that can be slid on. For the bearings inside the housing I also made a cover. To measure distance, I opened up digital calipers and cut slots in the sides to fix them with screws. Then I assembled them again. For the tailstock caliper, I mounted a bracket on the spindle bar. Then I fixed the caliper with 2 screws. You can now easily check the movement of the tailstock spindle. For the cross-slide, it is easy to add a digital caliper as well. I also added a plastic protection. For the carriage caliper, I added a slotted aluminium block to the caliper. The block is fixed to the lathe bed side, and the caliper head is screwed to the carriage plate. It's time for some testing. Here I use a 20 cm long aluminium rod. After drilling a center hole, the rod end can be secured by the live center. I can fix the tailstock by tightening the top plate bolts. To work on the rod end, I move the cutting tool to the other side of the tool holder. First I zero the cross-slide caliper and make a rough cut. Then I measure the rough cut diameter. To get a defined end cut diameter, I set the new cross-slide cut depth to 50% of the difference between the rough cut and the end cut diameter. The resulting end diameter is now exactly the target value. The surface finish is also quite nice. Let's cut some mild steel bar. Facing the steel bar works well. Let's make a 0.25 mm cut. The surface finish is not as nice as with the aluminium. After using a round cutting tool, the surface finish is much better. Let's drill a hole, first using the center drill and then using a 10 mm drill bit. This requires more force, so I use the threaded rod to push the tailstock spindle. Now we can do a parting cut. After de-sharpening the edges, the result looks quite okay. Finally, the lathe can be moved to the side of my working bench. Building a lathe is a big project and I learned a lot along the way. I probably want to add a compound slide for turning taper. I spent about 800 euros on this project and you could buy a small mini lathe for that money. But I wanted something small and I wanted a bigger spindle hole. And building something yourself is much more fun. I hope you enjoyed this video. Thanks for watching.